We've seen many instances already of heterogeneous equilibria, that is, involving multiple states of matter, that include solids dissolving in water. Just like the salt solutions we were recently discussing, a generalized solubility equilibrium typically looks like a solid breaking down into two or more ionic components, which are aqueous. So the solubility equilibrium constant for such an equilibrium is just the product concentrations, since we never include solids in the equilibrium expression. This K is called KSP for solubility product constant. And take, for example, calcium sulfate, or CaSO4. When this dissolves in water, we get Ca2 plus cations and SO4 2 minus anions, like so, with a KSP of 4.9 times 10 to the minus 5. So say I dissolve 0.005 moles of CaSO4 into 1 liter of water, and there's no precipitate left in the water. That is to say, the solid CaSO4 has completely dissolved into Ca2 plus and SO4 2 minus. So now the question is this system at equilibrium? I mean, the concentrations must be constant, right? Like, there's no way to add to the product side now. So by normal standards, that points to being equilibrated. But if I calculate the concentrations of my products, like here, and then I multiply those together, then I get something that's smaller than KSP, implying that we need more products to reach that ideal ratio. So in these solubility equilibria, equilibrium is achieved when we've reached the saturation point of the solution, as in the point where no more solid can be dissolved, and any excess exists as a precipitate. So if I took the same example as above, but just added more solid CaSO4 until I couldn't dissolve it any further, then the final product concentrations should each be the square root of KSP, or 0.007 molar. In rice table format, this whole process looks like this. And you may notice here that instead of X as the change variable, I used S. This S actually has a great meaning as a physical expression. S stands for the molar solubility of the solid, and it's a measure for how much solid is able to dissolve based on the reaction conditions. Molar solubility is always shown in units of moles per liter, but sometimes we use just plain solubility, and this can be in terms of grams per 100 milliliters or grams per milliliter, whatever. So unlike KSP, S is not a constant, as it depends on the reaction conditions. So for instance, the molar solubility of CaSO4 in water, like I've shown here, is going to differ from the molar solubility of calcium sulfate in a calcium hydroxide solution. Again, we've got a common ion problem here. Because we already have Ca2+ in solution, that's going to limit how much calcium sulfate can dissolve, lowering the molar solubility. Common ions aren't the only thing that have an effect on solubility, though. pH plays a large role as well. Say, for example, I have an acidic solution from HCl in water. HCl and CaSO4 share no common ions. However, SO4 2- is a weak base and will want to neutralize the excess protons from the acid. That means that as CaSO4 is dissolving, making more sulfate, or SO4 2-, the sulfate almost immediately gets used up, allowing for even more calcium sulfate to dissolve, generating a higher S value. This is really neat stuff and requires that you think ahead a little bit and decide how these combinations of different molecules will interact with each other.